Hello everyone, this is a new edition of the Kent seminar. We're starting it with Antoine Petit. Antoine Petit is a doctoral student in the Department of Civil and Environmental Engineering, and he works under Professor Ouyang. He got his master's from the UIUC, and he got his diplôme d'ingénieur from l'École Centrale de Lille in France. And his main focus now is on public transit network design and schedule control. He's graduating soon, too. Today he'll be talking to us about multi-line bus punching control via vehicle substitution. Let's welcome him with a warm round.
Thank you for the introduction, and thank you everyone for being here. Thank you ICT for also having me. It's a pleasure. So today I will be talking about a joint work with Dr. Lei and Professor Ouyang, which is about bus schedule control for multi-line transit systems. So reliability in transit networks, it refers to the consistency in vehicle headways, arrival times, and schedules. In fact, according to a survey that was conducted among American transit users, who were asked the question, what would motivate you to take public transit more often? The number one answer was provide a more reliable service. So it is crucial for the agencies to design systems that have consistent headways and vehicle arrival times if they want to ensure a good level of service and also a viable ridership. But because most bus lines operate within general traffic, which is obviously subject to congestion, and also have a dwell time that's based on a random number of users that would show up at each stop, then transit system can be very unreliable. Then let's look at the root of the problem. In a real setting, essentially random disturbances are due to traffic, passenger demand, and that gives rise to discrepancies between the actual arrival time and the scheduled ones. And those discrepancies are going to grow rapidly into large schedule deviations. In fact, it was proven in the literature that transit systems are inherently unreliable. The vehicles tend to pair or bunch, which create gaps in the system. To illustrate this, let me just show you an animation that I created. It's inspired by Professor D'Agonzo's work at UC Berkeley. Essentially, the circle here represents a bus line. Oh, can you see? Yes, so the circle here represents a bus line. The black dots are the buses, and the spikes are essentially the line of passengers waiting at each stop. So at the beginning of this simulation, the buses are obviously evenly spaced, the headway is constant, but as passenger randomly arrives at the stops, you're going to start to see some gaps in the system. For instance, this bus number 7 here already has a lot more passengers to pick up than this one, which you can see it's going to be delayed. And then at the same time, bus number 6 is going to be able to catch up. And then soon, eventually, those two buses are going to bunch. So that's what bunching is. A little bit longer, but essentially, as you can see, the gap in front of bus number 7 is getting bigger and bigger because the bus number 7 has to pick up more and more passengers. So that can create, first of all, frustration, and also because when buses are late, you have more people who are boarding, then those buses travel, you would tend to travel on crowded buses when you get on the late bus. And then because these buses are getting more and more crowded, they travel at a slower speed, which is also bad in terms of mobility. It also has negative impact on the society and the provider because transit users would perceive such systems as not providing a good level of service. And then eventually that would lead to people just dropping the system. So how do transit agency try to mitigate this problem? First of all, they use automatic vehicle location, for instance GPS, to track and locate buses in real time. The drivers also use communication devices to contact the dispatchers in case they're running late or if they are reaching capacity. Also, as I said, reliability is extremely important, and therefore many strategies exist. Most of them fall in the holding strategy category. They essentially consist in inserting some slack in the schedule. to hold the early buses at the stops. But the problem is that those strategies would cause more delay for the onboard passengers. You probably experienced that when you were on the bus. You were just waiting at the stop. The bus was not moving. Nobody was getting on or off, but yet the bus was, staying at the stop for some unknown reason at that time. So that obviously must be frustrating for the users. And yet this strategy is actually widely used in practice. Other strategies are called manipulation strategies. They consist in either skipping some stops to make up for the delay, or just allowing limited boarding. But again, those strategies are creating delay and frustration for the passenger, especially those whose stop is either skipped or has limited boarding. And finally, the strategy that we are interested in, the substitution, is an alternative approach that we'll actually explore here. So let me explain how that will work. So imagine back to this bus line, we have bus number 7 that's getting later and later. So essentially what we do is we say, okay, in 3 minutes, bus number 7 is supposed to be here instead of there. So what we're going to do is we're going to use a standby bus. We're going to insert it, and it's going to become the new bus number 7. Then bus number 7 is going to be put as not in service mode, which means it's only going to be allowed to drop off the onboard passengers, but nobody would be allowed to get on the bus. So that's probably why you've been seeing not in service buses on campus. What regularly, probably. So as I said, CUMTD actually uses this method to control for the bunching. However, their management strategy has not really been optimized. It's rather greedy. They tend to insert buses once the bunching has occurred, and they also locate the standby buses based on the history of bunching locations. So they essentially have someone in the control room, if you've been there, who would just decide and make the dispatches more like in a myopic way. So the good thing about this strategy is that it does not affect the onboard passengers. You would never notice that the bus, or even the bus that you're on, would go not in service. And if you're waiting at the stop, you would also never know that the bus was just inserted, if it's on time or good for you. So this is also a rather easy method to implement compared to the other speed control or slack method strategies that are found in the literature. Just a few examples of some business questions that CUMTD is trying to answer, and that we are trying also to answer in this work. What does the optimal substitution policy look like? When do you decide to insert buses? When do you decide to insert buses? How many standby buses should you have? Where should they be positioned in your network so that the strategy is most efficient? So let's look at the big picture of the problem. We basically have a set of bus lines, a set of standby locations, some standby buses, some operating buses. Then we basically need to determine which bus will be substituted, which standby bus will be the new operating bus, and then once a bus is put not in service, where are we going to send it back to? Which standby location is it going to be sent back to? So again, following the process that I described in the previous slides. So just to summarize, we have 3 statuses for buses. Either they're operating, or if they are substituted, then they become not in service, then they're repositioned at some standby location, they become standby, and then they're ready for insertion again, so that they become operating again. So in this work, we consider multiple routes with given length, given demand and city. We know the operating fleet size, the cruising speed of the buses. We also have some parameters for the boarding time. And we assume infinite capacity. And then essentially we're just going to simplify this whole model. Just imagine that instead of the passenger being picked up or dropped off at the stop, we just assume they're being picked up and dropped off anywhere. Just for simplification, it doesn't really change much of the problem. So what it's going to do is that because of this assumption, the schedule, instead of looking like a line like this, then for the stop it's going to stay, it's basically just going to be straight lines. because the buses just keeps going. And then I'll skip also the derivation of the mathematical, but basically we can keep track of the location and the occupancy of each buses. And because there is this random noise term, which comes from the random arrival of the passenger, maybe the random behavior of the drivers, then instead of just following the schedule, the actual trajectory here of the buses, so this is obviously space, this is time, the trajectory of the buses, instead of following the schedule, is just going to be pretty messy, and then buses are going to bunch, and then, so this is what happens. So how does the substitution work and help alleviate this issue? Well, imagine that this is an operating bus. Again, this is time, this is space. Imagine that you have a bus that's getting later and later. This is its schedule. This is its actual trajectory. Well, obviously you want to substitute it and insert a bus somewhere here. So what's going to happen is you make a decision at T. I mean, the agency is going to make a decision at T to insert a bus. Obviously, the decision cannot happen instantaneously. There's going to be a little bit of a delay for the standby bus to go from its standby location to the actual insertion location. So once it's here, the new bus is operating. So it's basically like the deviation is reset to 0 at this moment. But in fact, this is what you see on your schedule when you check your phone. The bus is back on schedule, but in fact, you actually have two buses. You have this bus, which is operating until T plus delta and then becomes not in service, then can actually potentially catch up its delay because it's only allowing a line of the passengers and not boarding anymore, so it's catching up slowly. And you have another bus until it's empty. And then once it's empty, obviously it goes back to the standby location, and then the other bus is this one that just becomes from standby becomes operating at this point. Do you have any question of how the substitution works? All right, and then we also keep track of how many standby buses we have at each of the standby locations. So, how do we formulate this problem? Let's just imagine we have an infinite planning horizon, let's say like a whole day of operations, and we have a fixed step size. We say we look at the system every 10 minutes. Every 10 minutes we decide whether or not we need a substitution. So at 8, 8:10, 8:20, etc. And then again, we keep track of the position of all the buses in the system, their occupancy, also where the not in service buses are, if they're almost done, and also where are the standby buses. So we keep track of this whole thing. It's a pretty big state of the system. And at each time, so 8, 8:10, agency is going to decide whether or not to insert a bus, and also where does the not in service bus will be retired. So two decisions basically at each step for all the buses. We also obviously have some constraints. I won't go into the math, but basically we want to make sure that the substitution can actually happen. Essentially that within the next 10 minutes, the standby bus can actually reach that standby location, that insertion location, and also that as soon as a bus is not in service, we decide where it's going to be once it's empty, etc., etc. So we just ensure the feasibility of all the substitution process. In terms of the cost of the system, we're going to obviously try to minimize those costs, but I'm just going to detail them a little bit. So we want to ensure that the passengers don't experience too much delay, nor too much waiting time. So we try to compute the waiting cost, which is basically proportional to the headway between the buses, and also the delay. How late is the bus compared to its schedule? We also have some substitution costs that are related more to the operation of the buses. So basically, we need drivers, we operate buses, they travel, we need fuel. So all these kind of costs are also considered in the model. And finally, we have some overhead costs that actually don't depend on the operations, but they are a pretty big portion of the cost. They include the driver wages. If your standby bus is really big, you need a lot of drivers. That's going to be extremely expensive, so we still want to account for that. And then finally, we have some depreciation costs just for the lost value of the buses. So eventually, we just formulate this problem as a stochastic infinite horizon problem and try to minimize those of user and agency costs that I just mentioned, subject to the system dynamics, the different constraints that I mentioned before, and the transition functions. How do we solve this problem? I won't go into too much detail. I don't know if you've heard about dynamic programming or approximate dynamic programming, but essentially the idea is that we try to approximate the objective function into a simpler function. So here we just simply use some piecewise linear function, and we try to have a nice, rather smooth objective function that we know. We use simulation to approximate this a little bit like machine learning those days. So we try to approximate this objective function and get a sense of what would be the optimal decision to make for the agency. And also, you might wonder, what if demand changes over time? That might also affect the whole problem. Well, we can address this time varying issue. Basically, when system settings change over time, we would just change the parameters of the problem and then solve it again using the previous model. But actually, what would be interesting when the demand changes is maybe adapt the configuration of your fleet. For instance, either having more operating buses or more standby buses. I mean, you can play with that to basically adjust to how the demand changes. So we're trying to be more flexible here. For instance, you can think of on campus, you have high demand during at the beginning of class time, but when classes are started, pretty much nobody's taking the bus anymore. So that can actually affect the whole operations. So I'll be presenting 4 examples each with different goals. The first example, I will show you what the policy looks like in a very simplified settings. The second example, I will try to illustrate benefit of pooling standby vehicles, basically having a fleet of standby vehicles that can be shared across multiple lines. The third example, I'll show you how we can adjust the fleet configuration to address changes in the demand. And finally, in the fourth example, I will apply the proposed strategy to a small CMTD-like network. All right, so here we're just considering, imagine just one bus line, just 2 operating buses, and we have 2 standby buses. So this, on the right, this will be the policy, the ideal policy. So what do I mean by policy? Imagine that this is basically the deviation of the bus. So 0 being the bus is on time, of bus 1, sorry. 0 bus 1 is on time, here 0 bus 2 is on time. So if the deviation increases, the bus is getting late. If the deviation decreases, that means the bus is getting early. Both are bad because that means the headway is increasing. So essentially, depending on the state of the system, which means the current deviation of both bus 1 and bus 2, we're going to have to make a decision. The agency is going to have to make a decision. So whether we have 2 standby buses or only 1 standby bus is available, that's going to affect our optimal decision. Basically, as long as the deviation is close to 0 for both buses, you do nothing. Like this is the white zone here, you do nothing. But as soon as the deviation of either bus increases or decreases, then you either substitute 1 bus or 2 buses, depending on, again, if you have 2 buses available, then yes, you can substitute both buses simultaneously. But if you only have 1 standby bus available, then you're going to need to substitute only 1. And now how does that reflect in the trajectory of the buses? So imagine this is time, this is the deviation, how the deviation changes over time. Well, you can see that when we apply this policy, as soon as the deviation grows large or too large, then we substitute and the deviation is reset to 0 right here, right there. So overall, we can contain the deviation of the system. So second example is basically a test case, and I'm trying to compare here the substitution strategy with some other strategies, either slack or speed control. Let me just present those strategies first. So speed control, essentially you have two types. You have the one-way looking. So basically, when a bus is operating, if it's getting later and later, you just adjust. You basically adjust the speed of the bus. So say the bus is getting late, so basically the driver is going to have to speed up the bus a little bit in order to catch up. If the bus is getting too early, then just slow down. Then the other option is the other strategy is the two-way looking strategy. Essentially now you take into account the distance, if you will, or the time between the bus ahead of you and the bus behind you, and basically try to adjust your speed depending on those two buses. So those, I just want to mention that those two strategies are basically state-of-the-art, so they're actually extremely, they perform actually extremely well. So we're trying to compete with this. I want to also stress again that although those strategies really help maintaining the schedule of the transit systems, they still affect the passengers because the bus slowing down or the bus, basically the bus slowing down is going to affect how fast you can reach your destination. So by using the substitution, we're trying to improve the user cost a little bit by, if you will, investing on more standby buses. So investing on agency resources. So let's imagine a network. So we have basically five networks with an increasing number of lines. So we have one bus line here, 2, 3, 4, 5, and we also increase the number of standby buses for each scenario. And then we're going to see that as the number of line increases, the cost per line for the substitution strategy is going to decrease. This is essentially because now we're pooling the standby buses. So pooling means that the standby buses are shared across all the lines, which is why the cost per line is going to decrease, while at the same time for the other strategies, having more lines is not really going to affect anything. So as you can see, as the number of lines increases, our strategy is doing better and better, and even getting close to compete with those state-of-the-art strategies. I won't detail too much, but basically, the good thing about our strategy is that the user costs are actually lower than for the one-way looking and two-way looking, basically 4 to 3% lower, and we're pretty much 6% off of the noiseless system, like a perfect system where there's no deviation, nothing, everything is on time. We're only, in terms of user costs, we're only 6% off. So it's a pretty good performance. All right. So in this example, we basically consider two time periods with different demand levels. I mentioned that earlier. One will represent basically an off-peak period, and the other one will represent a peak time period. So if we cycle over those two time periods, then that could pretty much represent a whole day of operation. You have the morning commute where there's a lot of demand, then between 10 and between 6 and 10, that would be a high peak, then lower demand, and then at the end, the evening commute, you have peak again. So basically, if you cycle over these, you have a whole day of operation. So we just consider those two time periods. And the objective will be to determine the optimal fleet size and fleet configuration between those two time periods. So how many standby buses, how many operating buses you should have. In addition, we will also consider the fact that you may have unused buses. So some buses might not even be needed. You leave them in the garage. So in that case, we just have lower depreciation costs, but you're just not operating them at all, so you don't even need a driver for that. Then we assume a few constraints, arbitrary, that I'm not going to mention here. And then we essentially just enumerate the cost, or we apply the whole, the whole framework that I presented earlier for each of those fleet configurations. We enumerate, and then eventually we can see that the optimal configuration would be to have during the off-peak 4 buses operating on each line, then 5 standby, and you left 1 bus unused. Then during the peak period, you have 5 operating buses on each line, and you only have 4 standby. So by adjusting your fleet, you can actually better address this demand variation issue. I actually just played a little bit with a small COTD network. I was trying to see, I asked COTD about what's their worst lines in terms of bunching, and those are basically yellow, the gold, the silver, the teal, and the green. You can probably recognize this is around the Union, this is your backline, this is the terminal. So this is essentially a subset of the lines of COTD. So we roughly know the different parameters, there's different settings for each of those lines. Then we apply this whole framework, and we can actually contain contain the deviation of each of those lines within 3.5 to 4 minutes. So only a 4-minute delay. Then we can also provide with some insights on how the standby buses are being used. So here, this is time, and this is how many standby buses you have on average at each standby location. So here you can easily identify which one are the most strategic ones. So let me just go back to here. So we have, I forgot to mention, we have 5 standby locations. Those are the black dots here, the red dots here. So here you can see that, I don't know if you can see, but basically location number 2 is the most popular one. And well, that's because it's located here. That's like really close to the Union. All buses actually go through the Union. So it's a very strategic place. So for COTD, it might be very useful to actually have some standby buses there. All right, so now I'll talk a little bit about my ongoing topic about resource planning for substitution strategy. We essentially want to revisit the model that I presented earlier and try to determine the critical input parameters for our substitution model, which are the fleet size and the standby parking locations. So fleet size is expensive. Parking locations are expensive. You need to pay rent for it, so we don't want to have too many of them. But at the same time, they need to be strategically located so that we can actually address this bunching issue more effectively. And then also having standby buses is expensive because actually the driver wages is extremely high compared to the rest of the cost in the system. So having more standby buses means that the agency has to put a lot of investment to ensure that the buses are on time. So we want to try to optimize how many standby buses we need to use. But the thing is that this problem is a little bit difficult. We cannot just plug this back into the whole problem because they have different time scale. The substitution strategy, the substitution decisions. So this part is basically the model that I presented earlier. It's basically a decision that you make every 10 minutes. But for the parking locations and the standby fleet, it's a longer time horizon basically. This is something you decide on more like a weekly or even yearly basis. So to address this issue, let me just first introduce the location problem. So it's about locating a number of facilities among a finite set of potential sites that aim at satisfying customer demand. We essentially try to minimize a linear combination of fixed facility cost and variable production and transportation cost to the customer. And we're actually interested in some extensions of this problem, which is when the facilities are capacitated, which means they have a fixed, a finite capacity, and also when the demand is stochastic. So why did I talk about this problem? Let's just try to see what's the analogy here. So imagine that the parking locations are the facilities from which we're going to provide the resources, the standby buses essentially. Then the transit stops become the customer locations, and the commodity is the buses. Then if the demand is represented by the number of substitutions that are needed at each of the stop, then you probably can see the analogy here. So capacity would be how many standby buses you have, and then just try to satisfy the demand, so satisfy the substitution by using the capacity of the facilities, so the standby locations basically. So there's an analogy here. So we're trying to make use of this models that they've developed for these kind of problems, for our transit-related problems. So our framework for solving this problem is a little bit complicated, but I'll try to simplify it. Essentially, we first assume a fixed standby fleet. Then we're gonna use the framework, the whole framework that I presented earlier, to estimate what's gonna be the demand. And a few other parameters that you don't have to worry about, but essentially we're trying to estimate what's the substitution demand when we have that many standby buses. So at each stop, we're going to gather data about how many substitutions need to be performed at these stops. This is going to be random, obviously, but we try to have some statistics about it. Once we know the demand, we're going to try to determine with a whole, again, an optimization model, where should we have our standby locations, basically. Then, once we know which standby location we need to use, we know the fleet size, then we can estimate the exact cost of the system by, again, going back to the framework I presented earlier, just deriving the policy and computing the cost of the system. This is a small test case that I played with just to show you guys. Basically, imagine you have two bus lines here, and you have a set. This is a little bit small, but so you have two bus lines, and you're trying to figure out where should we have our standby locations and how many buses should we have, standby buses should we have. So first, what I do is I look for the optimal. Not the optimal, I try to minimize the number of standby locations. So I try to find some sort of, using some sort of K-mean algorithm, where should, if we only have one standby location, where should it be so that we can reach everywhere in the network? Imagine we have stops here, where should that one standby location be so that we can reach everywhere? Then once I have this, I have the standby location, I know what's the fleet size, I apply the framework that I presented, I get some demand, I know what's the demand at each of those stops, then I use the complicated algorithm here, the optimization problem here, I determine where should which of those candidate standby locations should be used and which one should be just discarded. Then once we have this, we forget about this one, we know that the buses are going to be parked at these standby locations. Then we can derive the overall cost of the system. And then we iterate again and again, we can plot some points, then we just use some sort of approximation of the function, because we know that if you don't have enough buses, standby buses, the cost of the system is going to be huge, because you're going to have a lot of delay, a lot of bunching, so user costs are going to be huge. At the same time, if you have too many standby buses, your agency investments are going to be extremely high as well. So it should look like a curve like this. So basically, we just try to approximate this function here with a few points, and then we can figure out what's the optimal fleet size, and also based on the fleet size, we actually also know where are the ideal standby locations among the candidates that we have. All of this should basically answer most of the CRTD business questions that I mentioned at the beginning. So how do we do substitution? How many standby buses should we have? And also, where should we park those standby buses? I think that's all I have. So I think I went a little fast. So if you have any questions, please let me know.
What is your average monetary value of passenger hour, and how variable are all your results based on this value?
So remember in this slide, I mentioned some user cost and also some agency investments. So basically, we're just trying to get a homogeneous unit for this cost, right? Because passenger value is going to be in terms of time, but the agency investments are going to be in terms of dollar money. So we're trying to estimate. Imagine you're 10 minutes late. How much cost would that be? So for that we basically use some proportion of the wage, the minimum wage, to try to relate the lateness of the passengers, so how late you arrive at work, or maybe, I don't know, wherever you want to go, with some actual monetary cost, basically. So we try to reconcile the agency cost and the user cost using this monetary value, and it's usually related to the wage.
And how sensitive are your results if you change that monetary value?
Well, basically, because that's a good question. It's going to affect a little bit the results, because obviously if you increase the monetary value, then the system is going to tend towards, go towards trying to help the passengers more, right? Because if their value of time is higher, then we're going to need more substitutions. Obviously, if this monetary value is lower, then maybe we don't care as much about the passengers, so we're not going to need too many substitutions. But I feel like as long as the monetary value remains within a reasonable range, the overall policy is not going to change too much. Basically, if you think about a whole city, people earn very different amount of money. So we usually just try to take some sort of average of it. But going around this average is not going to affect the policy too much. If we only focus on the rich people, then yes, it's going to affect the substitution. But because we take some sort of average of it, then yes.
Can I make a comment? I think that's a very important question, and then if I may add to, I agree with everything you said, but then it will affect the policy. But the important thing is that actually our model is not like a one bullet to solve all problems for the world. This is actually a model we try to propose, and it can be calibrated and trained by any city that they care. And then for different cities, the result there will be some influence in terms of it's essentially how important people are compared to our own bus running cost. But then probably Anton, I think you can talk a little bit about how you train the model, and then how you can actually train the policy offline with existing. For every city, you can do the training, right? And then apply. So every city would actually calibrate the model for themselves, and then.
Yeah, this is just an input to our model, but
right.
It can differ from city to city. That's not going to affect our framework. We just say, oh, we have mu, then mu can be anything. Your city is going to decide what you want your mu to be. But basically, we can just, this model is going to run whatever mu we have, essentially. And if you actually, technically we could potentially have even a mu that's different from different passengers, depending on in the area where they are, basically. Here we're just trying to simplify things a little bit, so we only have one mu for everybody in the city. But you could have different mu's for different types of passengers. Yes.
I have a question. If you don't look at the strategic part of the model, like the second part of the model, do the overhead costs affect your optimal solution or your optimal value?
Not for the substitution policy.
They do not affect the optimal
because the substitution policy is really based on how late the passengers are, and also how much it costs to send a bus from one place to another. So it's more like in terms of fuel, depreciation of the bus because it's moving, that kind of cost. But the overhead, it's more to actually, that was a comment that we received, it's really just to fairly compare our strategy with say the speed control that doesn't require those standby buses.
Also, you showed that the comparison between your model and the two other policies.
Yes.
Yeah. So you said that with the increasing number of lines, the cost decreases. So is this assuming one substitution bus or?
No, we increase at the same time. We increase the number of standby buses.
Do you have an idea, like one standby bus, how long, for example, of a network it can serve?
So one constraint that I mentioned at the beginning was that we want to make sure that a standby bus can reach from where it is right now. It can reach the insertion location. So for our model to be able to work, we need to make sure that those standby buses, those standby locations, can actually reach the lines, basically, whatever to be substituted. So that's the only constraint we have. But then to reposition the bus once it's empty, then it can go wherever it wants. Wherever is optimal, obviously. But technically, it could go back wherever is optimal. But yeah, it's actually critical to be able to cover the whole area. So that's why we cannot just have one standby bus for the whole system. Yeah.
Thank you for the presentation on time. It's great work. So it seems to me that a lot of your inputs can be interpreted as random variable, like demand and something like that.
So yeah. So basically, how the whole. Yeah. Go ahead.
So as far as I understand, you incorporate all this uncertainty based on an additive noise assumption.
Sorry.
Additive noise assumption. You add a noise term.
Yeah.
So how realistic do you think that assumption is that you add an additive noise and you assume that every uncertainty is covered by that assumption, by that noise term?
That's a good
If
question.
if I understand correctly, the way that we are incorporating all the uncertainty.
Yeah, no, so that's a great question. Yeah, essentially all the trouble comes from this one term, the noise here.
Oh, okay.
Because of this noise, we have buses bunching, and then that's why we have to do this substitution. So everything does come from this. And actually, there's been a lot of research on this, and Professor Laganzo has been working on it, trying to derive the dynamics of the buses. So this is actually fairly accurate. The random noise is just trying to say, well, yeah, even though, buses have a schedule and everything, there's always going to be a little bit of a discrepancy between when the bus is supposed to arrive and when it's going to arrive. So there's going to be obviously a random noise. Then to know the statistics about this noise, that can be, here we're just assuming Gaussian, basically not just a normal distribution of the noise, but we can have wherever, like basically agency can collect data, try to estimate what's the distribution of the noise, and we can just plug it and then run the model.
Yes, and you sample from, so you said you do Monte Carlo, I couldn't understand that. You sample for some noise and you solve again and then you sample again. So how do Monte Carlo works?
Oh, yeah, I didn't talk about this, but Monte Carlo was in order to approximate the objective function.
Oh, okay.
So because there's a lot of randomness, we want to estimate the cost of the system, we need to do that a lot to have like an average value of it.
Oh, so you sample from that function and you approximate it and you solve that function in your dynamics program.
Yeah.
Okay, all right, now I understand. All right.
So when the not in service bus dispatch all the passengers, where will it go? Can it be used as a new standby bus?
Yeah. Sure. So imagine that this is the trajectory of an operating bus. So this is its schedule, right? This is its trajectory, and then the red lines here are just basically the delay of the passenger at each of the stops. So you can see this bus is getting later and later, but then here it's substituted. So that means it's not operating anymore. It becomes not in service. So it's only dropping off the remaining passenger. It doesn't drop them off right away. You still want passenger to reach their actual destination. So it's just going to keep running. It's going to be not in service, so nobody can actually board the bus. But the passenger who were supposed to alight at the next stops are actually going to alight. And because you're only alighting and not boarding anymore, the bus is going to be actually slightly faster than it's supposed to be. So it's going to catch up on its delay. It can even be early eventually. And then once it's empty, we reassign it to a standby location. So it does become a standby bus. So it's almost like a recycling process, but it's not the same bus that was in service. We just switched it in a way. But there's a little bit of a delay because we still have a few passengers to take care of in the meantime. Any other questions?
I think that's it. Thank you so much for your presentation.
I was trying to.
Run back. Thank you guys for coming. I have another journey.